So my name is Ramesh HG, Assistant Professor of Mathematics, Government Posted College, Chittoor. So in this session, I am going to explain definition of group and its properties with some examples. So we know what is the algebraic structure. So an algebraic structure is a non-empty set with one or two binary operations is called as an algebraic structure. So an algebraic structure G with binary operation star is called a group if it satisfies the following properties or rules. First you take an algebraic structure G, that is G is a non-empty set with binary operation star is called a group if it satisfies following axioms or rules or properties. First one is closure property or closure law, associative law, identity law and inverse law. Closure law means for all a comma b belongs to G, a star b belongs to G. Associative law means for all a comma b comma c belongs to G, a star b star c is equal to a star b star c. Identity law means for all a belongs to G, a star is equal to e star a is equal to a. And inverse law is for all a belongs to G, there exists a inverse belongs to G such that a star a inverse is equal to E. So what is the meaning of closure property first? What is the meaning of closure property? If you take any two elements in the G, if you take any two elements A, B in G, then A star B is also in G. If you take this product A star B first, then C, and B star C first and then C, then A, they are equal. And identity law, there is an element E called identity element such that A star is equal to E star is equal to A. And inverse property, so for each A belongs to G, there exists A inverse called as inverse of A belongs to G such that A star A inverse is equal to identity element. If these four properties are satisfied by an algebraic structure G, then G is called a group. So the algebraic structure G is called as group if and only if it satisfies these four properties: closure, associative, identity and inverse property. So another definition is abelian group. An algebraic structure G with binary operation star is called an abelian group. It is if it satisfies the following properties. You observe that abelian group is same as group except commutative property. So it satisfies closure, associative, identity, inverse. In addition to these four properties, it satisfies commutative law. That is A, B belongs to G, then A star B is equal to B star A. So an algebraic structure, an non-empty set G with binary operation star is called an abelian group if it satisfies all the five properties. Then it is called an abelian group. So the difference between group and abelian is only with the commutative property. So I will give some examples to understand what is the group and what is an abelian group. So set of all integers you take Z, it is denoted by Z. Set of all integers, it is denoted by Z. It is an abelian group under the binary operation as addition. So under the addition, Z becomes an abelian group. That means it satisfies all the properties: closure, associative, identity and inverse and commutative property, because it is an abelian group. So Z is equal to these numbers, and if you add any two numbers, 1 plus 2, 2 plus 3, minus 2 minus 1, minus 3 minus 2, minus 1 0, so all are integers. So it satisfies closure property. If you take 1 plus 2, 3, 3 plus 3, 6, or 2 plus 3, 5, 5 plus 1 is 6, like that. Minus 2 minus 1 is minus 3, minus 3 minus 3 is minus 6, or minus 3 minus 2 is minus 5, minus 1 is minus 6. So it satisfies clearly associative property. So one of the important element is 0. It acts as identity element in Z. And if you take 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, minus 1 plus 0 is minus 1, like that. So it acts as identity element in set of all integers. So that is 0 is called as the identity element under the addition in Z. And if you take inverse property, you observe that 1 we have minus 1, 2 we have minus 2, 3 we have minus 3, like that. 4 we have minus 4. So each element has its own inverse element and their sum is 0. 1 minus 1 0, 2 minus 2 0, 3 minus 3 0. So their sum is 0. So and hence it satisfies all the 4 properties: closure, associative, identity and inverse. And in addition to this, it satisfies commutative property also. So you observe that 2 plus 3 is equal to 3 plus 2, and minus 2 minus 1 is equal to minus 2 minus 1. So it satisfies commutative property also. Therefore, it is an abelian group under addition. Come to next problem. The set of all integers is not a group under multiplication. This one is important. The set of all integers is Z is not a group under multiplication. So it is not a group under multiplication, whereas it is a group under addition, but it is not a group under multiplication because so it satisfies even, closure, associative and identity element. That means 1 into 2 is 2, 1 into 3 is 3, 1 into 4 is 4. So 1 acts as identity element here under multiplication, but no element as inverse. If you take 2, it has no inverse under multiplication. 3, it has no inverse element under multiplication. So that their product is 1. 2 into some element is equal to 1. So it has no inverse element. It satisfies closure, associative and identity law. It does not satisfy inverse property. So therefore it is not a group. One more set is the set of all rational numbers Q is an abelian group under addition. So it is also it includes all fractions and integers, and it is an abelian group under addition. And here also 0 acts as identity element, and it satisfies closure, associative, identity. And here minus 1 by 3 acts as inverse of 1 by 3, and minus 2 by 3 acts as inverse of 2 by 3, like that. So each and every element has its own inverse. Therefore it is an abelian group under addition, and it also satisfies commutative property: a plus b is equal to b plus a. So it is an abelian group under addition. So therefore the set of all integers and set of all rational numbers, these are the two systems, number systems, are abelian group under addition. The set of all non-zero rationals, if you delete 0 from Q, this we call it as non-zero rationals, and it forms an abelian group under multiplication. So if you omit 0 from Q, then it forms an abelian group under multiplication, because it also satisfies all the properties: closure, associative, and 1 acts as the identity element, and 3 is the inverse of 1 by 3, or 1 by 3 is the inverse of 3, 2 by 3 is the inverse of 3 by 2, like that. Every element has its own inverse, and hence it satisfies all the properties of group, closure, associative, identity, inverse, and hence it is a abelian group under multiplication. The set of all real numbers R is also an abelian group under addition. So it is the union of rational and irrational numbers, and it satisfies all the properties: closure, associative, identity, and inverse, commutative property. Same like that, and 0 acts as identity element, and minus 2 is inverse of 2, minus 3 is inverse of 3, minus root 2 is inverse of root 2 minus root 5 is inverse of root 5, like that. So each and every element has its own inverse. Therefore, R is an abelian group under addition. The set of all real numbers, that is non-zero real numbers, they say non-zero real numbers. The set of all non-zero real numbers, R minus 0 is an abelian group under multiplication. Same as Q, it is also an abelian group under multiplication. R minus 0, if you delete R from 0 from R, then it called a non-zero real number, and it forms an abelian group under multiplication. So you observe that the set of all set of all integers, set of all rational numbers, set of all real numbers, set of all complex numbers, these are infinite sets as they contain infinite number of elements, and these are abelian groups. You come to finite set. The set of all fourth roots of unity is an abelian group under multiplication. So fourth root of unity means these are the roots of the equation x to the power 4 minus 1 equal to 0, and if you simplify x to the power 4 minus 1 equal to 0, x square minus 1 into x square plus 1, and solving those two equations we get 1 minus 1 I minus I, and if you put in the table form, so here 1 minus 1 I minus I, 1 minus 1 I minus I, and their product I will write here in this table. So you observe that and all these elements are the elements of G, therefore it satisfies closure property and associative property, and one acts as identity element. You observe that this is 1 into 1, 1 into minus 1, like this. So one acts as identity element. And what is inverse is 1. Inverse of 1 is 1, inverse of minus 1 is, inverse of minus 1 is minus 1, because minus 1 into minus 1 is plus 1, and inverse. So with this is I is imaginary number, I score is minus 1. You observe that I score is minus 1. I into I is minus 1, I score is minus 1. I into minus I is 1. So inverse of I is minus I, and inverse of minus I is I. So each and every element has its own inverse, and it also satisfies commutative property. You observe that the elements are symmetric about the diagonal. So this is a diagonal, and minus 1 I minus I, minus 1 I minus I, minus 1 I, minus I, minus I. So all the elements are symmetric about the diagonal, therefore it satisfies all the properties of a group, and hence it is an abelian group under multiplication. So this is another set cube roots of unity 1 omega square. So these are the solutions of the equation x cube minus 1 equal to 0 with the property omega cube is equal to 1. So I write all these elements here. You observe that this satisfies closure and associative property, and one acts as identity element, and inverse of omega is omega square. Inverse of omega square is omega. Therefore, it is an abelian group under multiplication. The set of all 2 cross 2 matrices over integers is a group under addition. So this is, you take a set of all 2 cross 2 matrices ABCD, with ABCD are integers, then it satisfies all the properties closure, associative, identity, inverse, and it is a commutative property also under addition. Therefore, it is a group, abelian group under multiplication. So these are some examples of groups and definition of groups with some properties. And major sets are set of all integers, set of all rational numbers, set of all real numbers, and these are forms abelian group under addition. And the non-zero rationals, non-zero reals forms an abelian group under multiplication, and fourth roots of unity, cube roots of unity forms a abelian group under multiplication. These are good examples for algebraic structure group. Thank you.